Good morning, everyone. With immense pleasure and honor, I would like to invite our speaker, Dr. Sreerama Kumar R., Professor and Chair, Department of Electrical and Computer Engineering, King Abdulaziz University, Jeddah, Saudi Arabia. He is also a researcher in the Center of Research Excellence in Renewable Energy and Power System. He has received his B.Tech from NSS College of Engineering Palakkad in 1984, M.Tech from IIT Madras in 1986, and obtained his PhD in Electric Power System from Indian Institute of Science, Bangalore in 1992. He was the founder coordinator of National Institute of Technology Sikkim and the former professor and head of the department NIT Calicut. Professor Sreerama is the recipient of prestigious national award constituted by Indian Society of Technical Education for Promising Teacher for the year 2003. His major area of interest include power system computation, demand side management, smart grid, and power system dynamics and control. Now, I may request Dr. Sreerama Kumar sir to carry over the session. Over to you, sir.
Dear Chairman Dr. Rizul Ramchand, FDP coordinators Dr. Sunita, Dr. Gopakumar, Dr. Deepak, dear friends and participants, good morning to all of you. Thank you, Dr. Sunita, for giving me an opportunity to be with all of you today in this auspicious occasion of the commencement of our faculty development program. Today, in this presentation, what we are going to see is an overview of wide area monitoring and intelligent control of power systems. Dear friends, we all know that power system is just less than 140 years old. As we know, the first power system was established by Thomas Alva Edison and his team in 1882 in the Manhattan City, New York. From that period onwards, our power systems are just evolving. Till recently, most of the power systems were following a regulated structure of power system operation and control as shown in this slide. We see that there are various components like generation, transmission, distribution. All these things are in this regulated, traditional regulated industry. All these are under the same utility, under the same umbrella, just like our state, Kerala State Electricity Board. But since 1990s, a major change is taking place in various utilities throughout the world. This is a conversion from the regulated structure to a deregulated structure of power system operation as shown in this slide. So these changes were in tune with the wave of what is called LPG. What is LPG? Liberalization, privatization, globalization, and that was happening during that period in almost all sectors in various countries throughout the world. In this new environment, electricity is considered as a commodity. Today, now towards this implementation of this new structure, the first major step to be introduced is to trifurcate the setup in the regulated structure into generation companies, transmission companies, and distribution companies. And now the utility can privatize each part independent of other parts. So now each one of us can have our own generation company, and the transmission and distribution companies can be with the company themselves. For example, Electric KSEB can have their Transco and Disco with them, the electrical network with them. Now, consumers can purchase the electricity from any company of their choice. For example, me, Dr. Gopakumar and Dr. Deepak, each one of us have our own company. Suppose now NIT Calicut is getting power from my company. But in the next month, if NITC is not happy with the services provided by my company, they can very well change to Dr. Deepak company. So thus, we have introduced a computation in this particular setup. Now here, as electricity is considered as a commodity, in the electricity market, just like in any other market, one of the major advantage expected out of this competitive structure is the reduced electricity bill together with better service. In order to survive in this competitive environment, we know that the companies will try to minimize the system losses. They will try to implement energy conservation measures. They will ensure power quality. And more than everything, they will ensure good service to the consumers for their survival in this electricity market. In fact, we can see that this is a shift from a monopolistic structure to a competitive structure. Now, during these days, particularly during this decade, we see another wave of change that is taking place in the operation and control of power system, and this is referred to as the smart grid environment, as shown in this slide. We observe that in this new environment, in addition to the conventional thermal power plants, nuclear power plants, hydropower plants, etc., we have the renewable energy resources also getting penetrated into the system in a significant manner. So the solar PV systems, wind energy conversion systems, etc., will be a part of the generation. In addition to that, we observe that there is battery energy storage systems, electric vehicles also. Now, whatever power that is generated in this power stations, that will be taken through the transmission lines and through the substations, distribution systems, etc., to the consumer premises. When we reach the consumer premises, here also we observe that there are renewable energy resources, distributed energy resources here also. So what we observe is that earlier the power flow was from the source to through the transmission distribution network to the load side. But now here from the load we are generating power through the renewable energy resources, and then we are injecting back to the grid. So there is a two-way power flow. So our system, the smart grid environment, has to take care of this two-way power flow. In addition to it, the blue lines that we see observe here, that represents the information flow. So here the communication earlier, it was from the source through the grid to the consumer, but now we are able to communicate. Two-way communication is also has to be incorporated. So here the companies will do the load forecast in the grid operation, and based on the load forecast, the operator will be communicating to the load side based on the market, that we can introduce some dynamic pricing kind of thing, and then the load or the consumers will be informed, okay, this is your electricity price, depending on whether it is a off-peak period or a peak period, etc. Therefore, this kind of based on that one, the people here in the residential building or the industrial building, they will be able to adjust their load. So load management would be possible on an online manner based on the input they are getting from the grid operation. And again, they will be able to communicate with this grid also in the similar manner. Okay, there are certain issues like this one, so they can communicate and then we can get it rectified. So this is a two-way communication, different from the traditional grid. And the green lines indicate that it's a charging, discharging that's happening in the customer premises. From the previous slide, we can observe one of the major features of a smart grid is the application of recent developments in computer and communication technologies in electrical power systems. Further, there are a lot of deployment of smart meters which will ensure that the two-way power flow is feasible. And again, there are a lot of deployment of intelligent devices also in the smart grid environment. Another major feature is the enhancement of system control through flexible AC transmission system devices and custom power devices such as static wire compensators, thyristor control series capacitors, unified power controllers, and so on and so forth. And as we have seen, it's a two-way communication that is to be embedded in a smart grid environment. And the demand response and the smart grid enabled demand side management has to be incorporated. Electrical vehicles give a major challenge to the implementation of smart grid. More than everything, the major challenge that we have to take care in a smart grid environment is the large-scale integration of renewable energy resources. And the main problem issue is the uncertainty of these renewable energy sources. We don't know what time the light, the solar light will be available, wind velocity will be available. This kind of uncertainty is there. So this makes the control system, traditional controllers, more difficult to operate in a conventional way. So it is very important and that we must go for more fast and accurate monitoring and control system. So in this presentation, what we are going to see is a highlight of the wide area monitoring and intelligent control of power system, and particularly related to the stability and security in the smart grid environment. Till now, even now, in fact, many of the utilities utilize unsynchronized measurements, and this unsynchronized measurements, you can see this is location 1 and this is location 2. Now, the magnitude of the two phases here, this is the voltage for phaser, for example, this is another voltage phaser here. We want to measure the magnitude of this phases. It is possible to obtain the magnitude of the two phases, and we can do the measurements in an unsynchronized manner independently. But at the same time, our focus, if it is to measure the phase angle difference, it cannot be done without a synchronization of these measurements. So a synchronized measurement facility is necessary, and as shown in this one, for example, the phase angle. So this is the timestamp. We have to see that what is the phase angle difference in these 2 points. So this is station 1, location 1, the phase angle is alpha 1. This is station 2, the phase angle is alpha 2. We want to know what is the phase angle difference between these two. Means there should be a timestamp. Both these phases are to be measured at the same instant. Therefore, so they have to be, these local measurements are to be synchronized, and this is done by means of GPS satellites. GPS means Global Positioning System satellites. This figure indicates an overview of a wide area monitoring system. What we have here is the phaser measurement units. The phaser measurement units, PMUs, performs the synchronized measurements continuously. So these local measurements, the timestamp obtained from this local clock of these PMUs, these are synchronized with all other PMU clocks. Consider this PMU measurement, and this measurement, this measurement, and this measurement. All these are to be synchronized together, and this is done using the GPS satellite signal. Now, the magnitude and the angle information that is measured by these PMUs are transmitted to the local substation and also to the state load dispatch center through the satellite every 20 to 40 milliseconds along with this timestamp. Now here what we, in the wide area monitoring system, what we have is a phaser data concentrator. This is a PDC, and this collects the input from PMUs such as the voltage and current magnitude and phase angle and the frequency from various substations, and this will collect and correlate the data, feeds it to WAMS and analytical function. So the analytical function means we can do the forecast, and then we could do the power flow analysis, stability analysis, assessment, and all that. And we can provide phaser data visualization, and data we can store for the past history terms. We can store for further refinement in the control action, and the system controls will be initiated based on the input that it gets from the PDC through these modules. The smart grid communication, the centralized communication is control system, is one method of system control in which we have many sensors deployed throughout the system, and these sensors will be communicating to with the local centers, local substations, as well as the distributed control station, as shown in this diagram. But we observe that this traditional centralized architecture, it becomes difficult because nowadays, particularly in the smart grid environment, there are a tremendous increase in the volume of data, and this centralized control system is not designed to handle this amount of data. For instance, consider the Western US utility, and maybe 2-3 years before, they had to acquire 8 million data points from 130 plus substations, and 7,000 field devices were there. So these data we have to transport and present it to the users at 35 plus control centers, and pass the data to various service centers like energy management center, demand management service, operation maintenance service, and other high level systems. So that's what we observe is that given the volume of data and the response time that is needed to control the dynamically changing grid, there is not enough time to transport the data to a centralized location. And making a decision and return a control command, it becomes a time-consuming task. So grid must be able to analyze the data, make decisions, and take control action even when the communication lines are down. This is very important, particularly in the emergency control situations. Therefore, we have to go for a solution, a better solution, that is a distributed intelligent control system. Now this diagram shows an autonomous intelligent control system. So we have local intelligent controllers, and this set of sensors will be interacting with this intelligent control, and this set of sensors will be interacting with this intelligent control. So based on the requirement, these controllers will be doing the control and remedial actions by themselves, and then later it may be able to communicating with the central control system. So this is a kind of autonomous control system to be implemented in a smart grid environment for a better control and operation of power systems. When we talk about intelligent control, what are the major attributes of intelligence? One particular aspect is that we are able to learn from our own experience. So ability to learn from experience is to be incorporated in our intelligent control. Another major attribute is that we are able to make crisp, clear decisions in spite of imprecise and vague environment, the real situations. Most of the real situations are imprecise and vague, but still we are able to take very crisp decisions. For instance, in power systems, suppose we have a microgrid, and then we say if the PV station output is very low and the wind station output is very high, then we assign the battery energy station D kilowatt to medium. So this this way we are able to make decisions like this one. Not that is exactly, we don't have the exact picture of what the output is, what the solar power output is, what the wind velocity is, but still we are able to make this kind of decisions based on this fuzzy decision making process. So this is the way that we can incorporate in the artificial intelligence technique, that is fuzzy control. And another observation of an intelligence is that ability to optimize the effectiveness of any activity. So for example, genetic algorithm is an evolutionary algorithm which optimizes based on the basic evolutionary procedures such as survival of the fittest. Similarly, there are many kinds of algorithms like a particle swarm optimization, simulated annealing, and colony algorithm, honeybee algorithm, like that. Therefore, in this presentation, we are not focusing on the fuzzy system or evolutionary algorithms that is related to making crisp decisions or optimization kind of thing. Mainly, we focus on the learning part, that is artificial neural network part, because this faculty development program focuses more on this aspect. This figure shows an artificial neuron, the basic element in a artificial neural network. As we see in this diagram, this neuron gets inputs x1, x2, x3 from the environment through some interconnections. And these interconnections has an associated strength or weight, and these weights are W1, W2, W3. So the neuron, artificial neuron, what it does is the weighted sum of inputs like W1 x1 plus W2 x2 plus W3 x3. It comes here. This is the weighted sum of inputs, and this is taken through an activation function. Here, the activation function that is used here is a threshold logic. If the weighted sum is more than some value, goes beyond this value, the output will be 1, otherwise the output will be 0. So this is one kind of activation function. When we go through the scan through the literature, we see that most of the literature, the most popular activation function that is used is a sigmoid activation function, as shown in this diagram. It is a nonlinear function. The maximum is tending to be 1, minimum is tending to be 0, and the function is given by 1 plus e raised to minus x. And this is a unipolar function because it is 0 to 1. Variation is between 0 to 1. Tan function is another activation function which is bipolar. It is between, variation is between -1 and to +1. So the function is given by e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. So this is a nonlinear activation function, whereas if the function is a linear function, the x and y is a linear function, so there is no point in utilizing a nonlinear function. We can use just a linear activation function is sufficient. In an artificial neural network, what it does is it utilizes a very large number of very simple processing elements, which will be doing a simple arithmetic or a summation or application of an activation function like that, and they come up with a network that has considerable collective computational abilities. So the key features of artificial neural network, it is done, see, when an artificial neural network gets some input, it will be processed in a parallel and distributed manner by so many neurons and interconnections throughout the network. So one particular advantage is that it has a very high computational rate when we compare with the conventional technique. Another important factor is that it has fault tolerance. What is meant by fault tolerance? Even if some of the neurons get damaged in the manufacturing process, or even if some of the new interconnections get damaged, but still we get the output more or less very accurately, because the processing is done by so many neurons and interconnections. So in a distributed parallel way. So fault tolerance is a major attribute of artificial neural network. As we have seen, it has a learning capability. We will discuss about this learning capability in the next few slides. And it is non-algorithmic nature. We can train the network to do a particular task. Once it learns the input-output relationship, like this one, through the learning capability, then it is non-algorithmic nature. That is, it is non-iterative. Once we give the input, immediately we will be getting the output. It is just application of some activation function just and then a distributed kind of weighted sum of inputs and application of activation function. Finally, we get the output. It is almost instantaneous. So this is a kind of artificial neural network. This is called a multi-layer feed-forward artificial neural network. We have the inputs x1, x2, x3, and the neurons are arranged in layers like input layer, hidden layer, and output layer. And the input x1, x2, x3 are given to the input layer. And these neurons in the input layer, each one is interconnected with each of the neuron in the hidden layer. And similar is the case from the hidden layer to the output layer. So this is called feed forward, means the signal will be going from the input layer to the output layer through the hidden layer as shown in this diagram. Now, for training the artificial neural network, what we do is we generate a input-output pattern training set. A set of patterns will be generated and kept with us, a list. For example, first list, x1, x2, x3, corresponding to that, suppose we know the output is y1. So this is one input-output set. Second input, x1, x2, x3, output is y2. That is second training pattern. Like that, suppose we have 10 input-output patterns with us. Then what next stages, what we have to do is we have to give initialize the weights, interconnection weights. So for example, this is 1, 2, 3, and this is 4, 5. So this interconnection has a weight W14. This is W15. This is W16. Similarly, this is 2. This is 4. So 2 W24, W25, W26. Like that, this is we can consider this as a weight matrix. So the next step is to initialize this weight matrix, the input to hidden layer weight matrix and the hidden layer to output layer weight matrix to some random values. So once we give the input first training set, input x1, x2, x3, this assume that these are all sigmoid activation functions we have introduced here. Therefore, it will do the weighted sum of these inputs and apply the sigmoid function as the activation function, and like that we get some neural network output y1 network. So we know the actual output y1, and this is the network output y1 dashed, and definitely this y1 dashed will be different from the actual y1. So what we do is we have an error that is generated out of it. This error will be propagated back from the hidden output layer to the hidden layer, and then from the hidden layer to the input layer. During this period, during this instance, what we do is this weight matrix will be adjusted. W will be adjusted to W plus delta W, such that this will be modified, and finally what we see through some learning algorithm, and then for this x1, x2, x3, the output will be exactly matching with the actual output. Then what we do, we give the next input output pattern, and then there will be error, and this error will be propagated back. The weight matrices will be again adjusted, and then finally up to 1 to 10 input output patterns, we have all the input output patterns we have shown to the network, and this corresponds to one iteration or one epoch. Now we repeat this procedure and several times. The same input output patterns will be shown to the network several times, and later we observe that the change in the weight matrices will become becomes smaller and smaller, and ultimately these weight matrices get saturated, and from that point onwards we observe that whatever be the input, the output would be corresponding output we can get. It means that this network has learned the input output patterns perfectly well. This is the way in fact we teach our children. So we show the child that okay, this is a red ball, this is a green ball, this is a blue ball, like that, and then after several exposure like this one, the child learns this. Okay, this is a red ball. Whenever she observes that this is a red ball, she says this is red and this is blue. Like that, it is possible to learn. So this is referred to as a supervised learning algorithm, and this is called error backpropagation learning algorithm. And this is a gradient descent technique that we have adopted in the error backpropagation learning algorithm, because we observe that we start from one particular initial solution, and then we reduce so through the error backpropagation learning algorithm, the error get reduced, and finally it reaches the global minimum, and then that will be the output corresponding to that particular input. So this is the gradient descent technique. Now this slide shows a typical example of application of multi-layer feed-forward neural network. This is called short-term load forecasting. It spans over from 1 hour up to a few days, and as we are power system engineers, and we know that this is mainly utilized for generation scheduling and security assessment. And the conventional way what we do is the time series model. Statistical models will be utilized, such as autoregressive moving average, models, etc. would be utilized for this forecasting. And here what we see is the one kind of neural network that is applied for short-term load forecasting. The input is x1 to x1. There are 7 inputs, and x1 to x1 means load demand of the last 7 days at hour j. So this short term, so today, what we want is, today now it is the time is 10:30, and now tomorrow at 10:30, what is the output we want to know. So what we do is, for the last 7 days, including today, 10:30 instant, we give the load data. That is every substation we have the load data, hourly load data will be available, and based on this information already available, we give this 10:30 a.m. Time load data to the network, and we already know corresponding to this one what are the outputs. So we can train the network using error backpropagation learning algorithm based on the past history data. Now today we give this input, and the network will be coming out as the output. So here the interconnection. So through the error backpropagation learning algorithm, we have already learned, the network has already learned the weight matrix W1, W2, W3, and the activation functions are known. Therefore, give the input 7 instance, and the next instant output will be available to us. So the load data for 2.5 months were utilized for training the network, and hourly system load variation was 2431 to 3151 megawatt. So if the load variation is in this range, it will be we will be getting the correct output once it is properly trained. Then following this multi-layer feed-forward artificial neural network using error backpropagation learning algorithm, another good development that I have seen in the literature is the development of radial basis artificial neural network. Even this is also a feed-forward network. Only difference is that instead of the sigmoid or a tanh activation functions, here we use a radial basis function. So the advantage of having a radial basis function, it is observed that the convergence of the learning is very faster. The number of iterations required to train the network to get the input-output relationship is very, very fast actually. Number of iterations can be significantly reduced in this case. And the output layer is the activation function. Here it is the sigmoid, not sigmoid, a radial basis function. Okay. Now, a deep neural network has more hidden layers that give deep learning a more powerful ability to represent the complex relationship. In fact, compared to an artificial neural network, a feed-forward network, it has more number of hidden layers. So this is then, if it a feed-forward network, we say a deep neural network like this one. The hidden layer is introduced in order, if the input-output relationship, we know that it is a nonlinear function. If it is not a nonlinear function, no need of any hidden layers. But then the nonlinearity is too significant. It is better to capture this nonlinearity. It is better to have more hidden layers, and like that, then it is we say that it is a deep neural network. But one particular issue with this deep neural network is that the conventional error backpropagation learning algorithm cannot be applied to this one if we don't have a proper initialized weights. In the traditional way, what we do is that the weight matrices will be initialized to random values through random number generation. But here it is not possible. If you are giving some random initialization to the weight matrices, it will not converge. So 2006, Hinton had come up with an algorithm that's called greedy layer-wise pre-training method, and this was a milestone for the development of a deep learning, because this will give the initial weight matrices, that is a pre-training method. So this will be given, assigned to them, therefore the learning can be done for the deep neural network. The feed-forward network, we have, whatever we have seen is a feed-forward network, and there are feedback network also. For example, Elman recurrent network, long and short-term memory network, like that. In a feedback network, what we have is that, so for example, consider this neuron, we take the output of the neuron and then it can be fed back. This is one way of feeding back to the network. And then another one is we may take the signal from the output layer and it can be taken back to the hidden layer, or from the hidden layer to the input layer, and so on and so forth. And this is actually through the implementation of the feedback, what we really do is we are introducing some kind of memory into the network. So the advantage is that the output that we get here will not be decided only based on the current instant, but on the past history also. So it can be certain places, the control action can be better. The forecasting can be made better than the traditional backpropagation learning algorithms. Elman recurrent network is a recurrent network, and you can see there is a feedback from this hidden layer to this hidden layer. Similarly, long short-term memory LSTM and ANN is also a kind of recurrent neural network. Any neural network that is introduced like this one, it will have its own learning mechanism, a learning algorithm, learning from the neural network point of view, and the training from the trainer point of view, our point of view, our perspective. When we scan through the literature, there are a large number of various kinds of artificial neural network topologies, such as recurrent network, Adeline, Bayesian network, co-field, sparse vector machines, coherence, self-organizing feature map, deep neural network, and so on and so forth. And I'm not going to discuss each and every one of this one, but then most of these important things will be discussed in the faculty development program. So let us go to the next slide. The training of artificial neural network can be generally classified into supervised learning algorithms that we have already discussed related to the multi-layer feed-forward networks. Another one is unsupervised learning algorithm. In the literature, the computative learning is a typical learning of this kind, and another learning algorithm is referred to as reinforced learning algorithms. Now, coming to the computative unsupervised learning algorithm, let us consider this diagram, this network. It has an input layer and a computative layer. This computative layer, neurons, each neuron in the computative layer has a weight vector associated with it. The weight vector, for example, consider this network. This has input W1, so this is 1, this is say 4, 1, 4, W2, 4, W3, 4, like that. So this is the weight vector associated with it. So each neuron has corresponding weight vectors. Now we give the input x1, x2, x3. So x1, x2, x3 form the input vector. So in the computative unsupervised learning, what it does is it calculates a similarity measure between this input vector x1, x2, x3 with the weight vector of each neuron in the computative layer. So for every input vector, the computative neuron compete with each other to see which one of them is the most similar to that particular input vector. That is, it operates as a winner takes all strategy. So this checks whether this is more closer to this, the algorithm checks whether this is more closer to this weight vector, whether the weight vector corresponding to this one is more closer to this input vector, and so on and so forth, and like this one. And what it does is the winning neuron sets its input to 1. If this weight vector is more closer to this input vector, the output of this neuron will be 1, and these outputs will be 0. So like that. So next instant, next input set will be given, and then the most competent neuron will be getting we will be getting the output like this one. So the Euclidean distance is utilized in the computative learning to know whether which neuron is more closer to the input vector. So we observe that here we give only the input and we get the output. Actually, this kind of learning is mainly utilized for clustering purposes. For example, suppose we have red balls, green balls, and blue balls. So we show this input pattern. Say red ball means it will be clustered to this kind of red, blue, and green balls like this one. In the supervised learning, what we give an instant of the input, and the network learns the mapping of the input instant to the corresponding output through the input-output patterns that we give. But at the same time, in unsupervised learning, we give an instance, but if we give only the input patterns, no output is given. But at the same time, it will be able to classify it to the various clusters. Each instant will be classified or clustered to various groups. In the reinforcement learning, it is very interesting to note that we are not giving a particular instant, but we give certain goals as the input. And the network learns a sequence of actions to meet the goal, and the output will be a sequence of actions like this one. And this is achieved through an evaluation reward penalty process. We do these actions through the creation of an agent. So the reinforcement learning doesn't use an existing data set. Instead, we create an agent to collect its own data through trial and error in an environment where it is reinforced with a reward. So this is the reinforcement learning agent. It's a learning and decision-making agent. It is away from the environment, and it observes what is happening in the environment, and this takes action based on the policy that is already embedded by that the agent knows what are the policies. Now, based on this, it does certain action, and this action can improve the situation in this environment, and if it improves, it will be giving a reward to the agent. If it is not good, if it affects badly, it will give a penalty to the agent. So the agent tries to increase the reward that it gets. Therefore, its actions will be modified accordingly, and finally, through this process, the agent will be learning the action to be taken based on the goals that we have already set to improve the system, the smart grid environment. So the process is observe the system environment, decide the action based on certain strategy, perform the actions accordingly, receive a reward or penalty depending on the effect of the action of the agent in the environment, learn from the experience and refine the strategy. Then iterate this one until an optimal strategy is found for a particular goal that is required. So once it learns, automatically it will perform the task without any change. Now, in this reinforcement learning, one important note that we have to take care is that being greedy doesn't always work. It means that there are things that are easy to do for instant gratification. But at the same time, we must note that there are also things that provide long-term rewards. The goal must not be greedy by looking for the quick, immediate rewards. On the other hand, we must focus to optimize the maximum reward over the whole training period. The reward the agent gets must not just depend on the current state, but the entire history of states are to be considered. So this is one important point that we have to take care. There are various learning algorithms, reinforcement learning algorithms available in the literature. The most common ones are the Q-learning algorithm and the SARSA, State Action Reward State Action Learning Algorithm. And these details, the algorithms will be discussed in our faculty development program. Another interesting development from the advanced algorithm that's called cooperative multi-agent reinforcement learning algorithm. What it does is instead of using a single agent, we can use many agents to perform a task. And these agents have to cooperate cooperatively to tackle a specific task. Each of these agents, they have the same goal. So the agents coordinate their actions to achieve the pre-designed goal. And the major benefit of this multi-agent cooperative reinforcement learning algorithm is that we can have fast computations. And another advantage is that we can add new agents easily in the system depending on the system requirements. So this is, and actually there's the cooperative multi-agent reinforcement learning algorithm has been applied in power system stability and smart grid environment as well. So this slide shows a general framework for intelligent voltage control through reinforcement learning. So this is the smart grid environment where we have a wind energy conversion system, solar energy conversion system, everything together, operating together with the thermal and hydro stations taken through the transmission systems and so on. It reaches the control, the load centers. Now the WAMS, wide area monitoring, through wide area monitoring and control system, we monitor the system variables, power, real power, reactive power, voltage, etc. And this will be given as the input to the agent. These are the observations of the agent for intelligent voltage control. And based on its input, there are certain policies for the agent, like adjust the generator voltage set points, adjust transformer tabs, adjust static voltage compensators, like that. And based on these policies, based on the state input, the state and the reward input, the agent performs certain intelligent control. As this intelligent control, it may improve the voltage profile in the system, and if it improves, the agent will get certain reward. Otherwise, it will be getting a penalty. So like that, just like what we have discussed in the previous slides, it will be learning the voltage control by itself automatically. And once it is learned, it learns the action plan, the strategy is identified, then the voltage control will be done by the agent at ease, and it will become automatic. The WAMS, wide area monitoring and intelligent control, has been applied for system-wide monitoring, islanding detection, loss of synchronism detection and control, and improving the system dynamics through emergency control. And this slide shows a typical framework for emergency control. So this is the server, WAMS server, and say for example, this is the measurement substation. It collects the measurements will be done, and it will be taken through the satellite, through the hub to the WAMS server. And the WAMS server and the supervisory control and data acquisition system, it performs the state estimation and filters out all the noises and all that. And finally, it will be interacting, it will be communicating the control action through the hub, through the satellite to various substations. For example, an islanding signal can be given to the substation, extra high voltage substation here, islanding signal can be given. Similarly, another emergency control, a load shedding signal can be given to the substations, specified substations like this one. So this is the general framework for the emergency control in case of any stability or security issues. Now, this framework, this is the framework for stability and security assessment. This module shows offline training module. We have historical database, and this that is from which we get the historical samples. And in addition to it, we have the samples generated out of our own simulation, our system simulation as well. So we train the network, artificial neural network, through the historical samples and the simulation samples. And then once it is trained, this network can be transferred to the control center, and this will be embedded in the control center like this one. Now this module is the WAMS module, and we have the WAMS server that which receives the inputs from the phasor measurement units and the phasor data concentrators, and then through this we get the real-time measurements. So this real-time measurements can be utilized for online updation of the artificial neural network that we have already transferred to the control center if it is necessary. Otherwise, the same network and the same learned network can be utilized for the stability or security status, to convey the status to the operator. Now, the operator can take the control action either manually or automatically based on the status that he receives from this neural network. That this neural network can be a software package or a chip that can be deployed in the control center. So now coming to the major challenges and the future directions of the WAMS and intelligent control in smart grid. One particular, even now, significant research is required because of the large-scale integration of the distributed energy resources and the battery energy the energy storage systems in the network. Coordinated scheduling of electrical vehicle charging and discharging is a major challenge, because a large number of electrical vehicles are going to be on the roads, and then charging, discharging management is a major challenge, particularly coordination, when to charge, when to discharge. This kind of things are to be properly done. Otherwise, it can become a heavy load in the system. The system collapse can take place. Similarly, generation forecasting, load forecasting, because particularly in the renewable energy resources, what would be the solar power output in the next instant, we don't know. But at the same time, we would be able to predict based on the past history. So this is forecasting is necessary. Load forecasting also is important, and then load balancing. So these are all major challenges as the system complexity is increasing because of the two-way communication, because of the large-scale integration of distributed energy resources like that. Another one is the system operators coordination, regional transmission network operator coordination. All these things require a lot of research even now. Still, research further refinement is required in the home energy management, information security, demand response, dynamic pricing, and so on and so forth. Now we know another major challenge each one of us has to take up is related to the millions of data from various measurements throughout the system. The number of sensors and the PMUs that we introduce into the network is becoming too much, and then because we have PMU networks, advanced metering infrastructure networks, sensor networks, each one of them have to interact with the WAMS server, and the big data analytics has to be incorporated together with the WAMS and intelligent control. So this is a major challenge. And in addition to these grid measurements, we have the weather data, because solar, wind, solar photovoltaic system data, solar irradiation, wind velocity data, geographical information system data, financial data. So all these things make our the computations really challenging, and we have to take care of this. We have to incorporate this big data analytics in the WAMS and intelligent control. This is our last slide, the AI platforms and development tools. Microsoft Azure AI platform, this is one of the most popular AI development platforms. And then IBM Watson is another platform which has already come up with several industry tailor-made setups for healthcare, oil and gas, advertising, financial services, etc. Google Cloud AI platform can be very well used for the AI development. Infosys NIA, Big ML, each one for production grade AI platforms. In an academic environment, we can definitely use MATLAB toolboxes like ANN toolbox, for CGA toolbox, and so on. Python programming, it is a thing that we can utilize for the development of artificial intelligence tool packages. And I think the definitely this FDP will be giving exposure to this one through the lab experiments, so that we will be familiar with this Python programming in this FDP. So with this few words, let me stop. Thank you very much. The email ID is given here, and the mobile number India is this one. This is the Saudi Arabia email, the mobile contact, and you can interact with me if you have any clarification that is required in my presentation. So thank you very much.